All right, here we are back for basically the second half of this chapter. Here we go. All right. 3C measurement of entropy. All right. So if S delta S is Cp natural log of Tf over Ti when there's a temperature change of a substance, right? And the delta S of a transition is delta H over T, right? Then the total entropy change would be the sum of all the heating and transition steps, right? Now, what we typically do is that we assume really that Cp is going to be constant, right? It's going to be constant over that entire range. In real life, that's not going to be true, right? Cp is going to be a function of the temperature, right? Like in this particular uh, section right here, right? We see the Cp changing quite a bit as the temperature changes, right? When we do our calculations, we kind of ignore that. But if you wanted to do that actually correctly, right, then you would have to basically integrate uh, Cp over this temperature change, and it would kind of go from there, right? So he says the variation of Cp over T with temperature for a sample is used to evaluate the entropy is equal to the area beneath the upper curve up to the corresponding temperature, right? Plus the entropy change right here. Notice this is very discrete, right? There's no temperature difference here, right? And then so on and so forth, right? The entropy denoted by the yellow dot on the yellow curve is given by the dark shaded area in the upper graph, right? All the entropy right up to this point is everything before it, right? Now, we keep it simple. We're not looking for that. Well, we're going to keep Cp to be assuming it to be constant, or maybe a function at the very worst. Right, but this is how we're going to measure it. Second. It doesn't want to go. Oh, there we go. Boop. There we go. Now, as I say here, summarize an entire page of the book, which is just extra for no reason. All right, the third law of thermodynamics states that the entropy of a perfect crystalline substance at zero is zero. Now, the entropy of a perfect crystalline substance is zero at 0 Kelvin. Right? I talked about that before. Right? We can use the absolute entropies of molecules to find the entropy of a reaction. Right? Delta S of a reaction is just S of the products minus the reactants. Right? S of the products minus reactants, same exact thing we had before, right? As H. Right? It was H of our products, right? The HFs of our products minus the HFs of our reactants, right? Same exact thing. Our absolute entropies, if you notice, are always going to be positive, right? These numbers right here are always going to be positive, right? Because we have a lower bound of zero. S always has to be positive, right? But delta S of the reaction can be positive or negative zero, right? It just depends how this subtraction works out. Now, again, this is just like delta H, exact same thing as delta H, and exactly the exact same thing as Cp, right? Cp, delta Cp of the reaction, which we did last topic and on the exam, I think, right? So I'm not going to do a question about this because this is the exact same thing as always, right? We've seen this multiple times. Just because it's S instead of H doesn't change the actual doing of it, right? Now, just like H, our heats of formation, right? Ions can't exist alone, right? And so the standard entropies are indexed against H plus in water, right? So the standard entropy of H plus in H2O liquid, right? That's going to be our zero. Again, just like with delta H or HF, I should say, Right, this is largely arbitrary, right? No physical or statistical basis, right? Like our absolute entropies, right? Our standard entropies, in this case, delta S, can be positive or negative. Right? So just to point that out, right? Because ions specifically can be positive or negative. Basically, everything else is going to be positive. All right. Now, entropy will change with our temperature. This is what we just finished up the last video with, right? Entropy at TF is equal to entropy at TI plus CP natural log of TF over TI. Right, if we wanted to apply this to an entire chemical reaction, right, we could still do that. Right? You know, delta S of the reaction now, instead of just being for individual components, now it's for an entire reaction, right? The CP will be for the entire reaction, right? Just like we did from last topic, which is still, right? Yeah, the same exact thing is still CP of products minus CP of reactants, right? Times the natural log of TF over TI. Right, so if you notice, this works exactly the same way that it worked with delta H. All right, we had an equivalent equation that was delta H of a reaction at TF equals delta S of a reaction, at TI, and then there was delta CP of a reaction times TF minus TI, right? That's what the delta H version was. And this is extremely, extremely similar. Sorry, this should be H. And they're so similar, I'm putting them all over the place, right? But this is exactly the same, working exactly the same way, right? So if you needed to do this, sometimes you'll need to calculate CP of the entire reaction and then plug it all in, right? It kind of goes from there. But it's exactly the same thing that we saw in the last chapter, just slightly different. We have natural log here instead of just TF minus TI. So we're not going to do that one of those too much. Okay? Now, when we get to topic 3D, concentrating on the system, this is going to be quite a bit short, to be honest. Okay? In the past, we've used Gibbs free energy. We used that in Chem 2. We said that delta G is equal to delta H plus T delta S. Right? Right? We know that delta G equals H plus T delta S. Right? And of course, we note that delta H is Q at constant pressure. Right? If we are instead at constant volume, right, Q is equal to delta U. Right? Q is equal to delta U. In the constant volume situation, right, we get an equivalent of delta G, which is called the Helmholtz energy. Right? So notice that these are basically exactly the same. Just this is at constant pressure, and this one is at constant volume. Okay. Same difference. They work exactly the same way. The one is at constant pressure and one is at constant volume. Right? And all goes back to what Q is at each different condition. Right? What Q is at each different condition. All right. So just like our Gibbs, right, a negative value for the Helmholtz energy is going to be a spontaneous process. Right? Just like our Gibbs free energy. Same difference, just constant volume instead of constant pressure. That's really all we're going to say about it. Right? Like H and S before, delta G is a state function. And so the Gibbs free energy of our reaction is going to be, again, products minus reactants. Right? Still products minus reactants. Very easy. Right? Every atom and molecule has a non-zero value for delta G. Right? It can be positive or negative. Right? It doesn't have to be just positive. It can be positive or negative, right? But it's going to be a non-zero value. And finally, like S before, we just saw delta G of our ions are still indexed against H plus. Right? Still indexed against H plus. So it's kind of all the same stuff. right? Now, for the rest of this section, I cut out all of the part about maximum work and then the Born equation, right? I looked at all the problems for it. I didn't really like the problems. I didn't really like, honestly, the concepts are super interesting to me. So I kind of skipped them all. Like, hey, guess what? I'm the teacher, so we can do that, right? So when it comes to section 3D, we only really care about, this and really these two, right? Good old delta G equals delta H plus T delta S, right? That's always very good. And then the Helmholtz equation, which is the equivalent in constant volume. So now let's go on to the last section. We're going to you're going to kind of fly through these sections because these middle sections are not super interesting, to be honest. We're combining the first and second laws to put it all together. All right, so if we take the first law of thermodynamics, right, this was U equals Q plus W, right? And we substitute in state function derivations of Q and W, right? So we know that Q equals TdS, right? Because ds equals Q over T, right? And we know that work equals negative P dV. And we know that from chapter 1, right? So if we put those in, right, now we have, right, T is a state function, S is a state function, P and V are both state functions, right? Everything's hunky-dory. Now we have all state functions instead of Q and W, which are not state functions. Put it all together, and then du is equal to T ds minus P dV. All right. So this more generalized equation, I guess we call it, right, gives us an equation that applies to any closed system, right? So energy is not going in or out with no additional non-expansion work, right? So that means no electrical work, nothing like that. All right, we kind of skipped over that portion in the very beginning of topic 2, I think. But there's electrical work, there's all other types of non-PDV work. And so we're not gonna include that yet, right? If we did, we would have to add an extra, we'd have to add an extra thing here, right? Like electrical work is going to be V times I, like the potential times the charge. I don't remember the actual variable symbols are, but we would have to just add it in basically, right? Now, in the middle of this section, there's lots of stuff about Maxwell relations, right? And they do this using lots and lots of different partial derivatives. Now, because we've figured out that partial derivatives are not in your background, right? We're going to mostly skip this, right? And also because they, as far as I've seen, have pretty limited applications, right? If we need something useful, right, we're going to, like, I'm just going to show you the actual relation, and we're just going to take that as is, right, on face value, and not worry about really where it came from. It's going to come from partial derivatives, basically, right? And also, there's a whole section about internal pressure, right? Skipping that too, because again, I don't really like internal pressure, and I don't like the questions that go along with it, right? I mean, if I look at all of these questions, like I don't think there's a single question when it comes to internal pressure in the entire book. So maybe in the problems, it's somewhere hidden in there, but it's fairly unimportant. We're going to skip it. All right. Now, if we wanted to do something similar for delta G, right, make it all into state functions or kind of different types of state functions, basically, right? G is a function of H, T, and S, right? Right, then the maximum change is going to be, right, dg equals dh minus t ds and then s dt. So this is g equals h plus ts. right? If we take a derivative of all these things, right, the change in G is dG, change in H is dH, right? And then TS, because of the, you take a derivative, you do 1 times the derivative of the second part, right? First part times the derivative of the second part, right? That's just doing a derivative of multiples like that, right? So we get this sort of definition, right? The definition of H is U plus PV. Right? If we plug that in, right, then we get du, right, dPV. And if we do dPV, that's going to be dPV and PdV. Again, we're doing like the derivative here of P times V. Then we have to do our multiple rules for our derivatives. So we get multiple things. Right? So we get a whole bunch of stuff here. Right? But if we know that du is TdS minus PdV, which we just figured out, right, one slide ago, that allows us to put this in for du. And when we do that, right, TdS cancels out with minus TdS. Right, negative PdV cancels out positive PdV. And what we're left with is dG being VdP minus SdT. Right, VdP minus SdT. And since pressure and temperature are variables very easily controlled in the chemistry lab, right? This highlights why Gibbs free energy is very, very prevalent in chemistry. But our Helmholtz is mostly, it says, mostly unknown. Right? If you wanted to look at the Helmholtz, this would be the equivalent version of it, right? You'd have to control the entropy. I don't even know how you do that. Controlling the volume, easier to do, right? But controlling the entropy, not very easy to do, right? That'd be very hard to do, right? But in this case, if we control the pressure, we control the temperature, both things very easy to do. We minimize dP and dt, the change in pressure and the change in temperature. And we get a very nice, simple equation, basically, for the change in Gibbs free energy. Right? Makes it much easier to use. All right. Here's examples or implications, I should say, that come from this. Right. If we look over here at pressure and the Gibbs free energy, right? This is looking at dP, how dP changes. Right? It says the variation of the Gibbs energy with the pressure is determined by the volume of the sample. Right? When we're looking at liquids and solids, which have very low compressibility, right? As we change the pressure, we don't see very much change at all in the volume of the liquid. Right? We don't see very much change in the volume of the liquid. And so, we would not expect to see much change in VG, right? If dP is pretty consistent, we wouldn't expect to see changes in dG, right? For gas, right, a gaseous, as it says, because the volume of the gaseous phase of the substance is greater than that of the same amount of liquid phase, and the volume of the solid phase is smallest, Gibbs energy changes most steeply for the gas phase, right? Because we expect gases to react more partially, I guess we'll call it, as we change our pressure, right? Because they start with such large molar volumes, they have a lot of room to move, right? And they're much more compressible. Right? If we look at temperature and Gibbs free energy, right? Says because the entropy of the gaseous phase of a substance is greater than that of the liquid phase, and the entropy of the solid phase is the smallest, the Gibbs free energy changes most steeply for the gas phase. Right? So the gas phase, because all this stuff is moving around, when we change the temperature, it has more entropy to change. So we'll call it that way, right? More entropy to change. Liquids and solids, not quite as much. Right? Liquid solids, not quite as much. But there's just a few short implications from this, just theory stuff, basically. Right? Now, getting back to something that's a little bit more useful, right? Through some mathematical chicanery, right? If you want to go look in the book, I'll give you a copy of the book. You can look it up, how they get to this particular outcome, Right. Anyways, we can describe the variation of the Gibbs energy with temperature. Right, the variation of the Gibbs energy with temperature. Right. So this here, just to load it out, this is literally what is called a DG divided by temperature. Right. So sometimes some notations will put like a dash because it means like you want it in terms of temperatures, like units like that. This is literally DG divided by temperature, and then over DT. Right, over DT. Right. If we apply this to any change, especially transitions, which will be useful because then we have a very constant delta H, right, and a constant temperature because it's equilibrium. Then our delta G over T over delta T constant pressure is this, right? Now, this whole thing looks kind of complicated. It's like delta G over T over delta T. Like it makes a lot of really kind of crazy stuff, right? Well, let's do an example of it to show you exactly how this would work. All right, so the change in the Gibbs free energy is found to fit the expression delta G equals negative 73.1 plus 42.8 T. All right, if we want to use that Gibbs-Helmholtz equation to calculate delta H for the process, right? So we have in here, we'll just do D delta G divided by T over delta T. Change this to be better. Right. All of that is equal to delta H over T squared, and it's going to be a negative delta H over T squared. Right. So in this case, what we're seeing here is that we're basically on the top portion. Delta G, right, is going to be negative 73.1 plus 42.8 T. All right, we're going to divide all of that by T, right, and then take the derivative of it with respect to T. I know I'm changing from these deltas to the D's back and forth, but they're all the same thing. All right, it's all derivatives, right? All right. So if I do that, what do I get? All right, if I do delta G, which is this equation, divided by T, I divide it all, I get negative 73.1 T, or 1 T to the minus 1, we'll call it that, plus 42.8. Right, and these T's cancel out. Right. We're going to take the derivative of this with regards to T. Right. If we do that, right, our power rule says, right, negative 1 is going to come out in front and then become negative 2. That's going to be a positive 73.1 T to the negative second. And then 42.8, just being a constant, is going to drop out. Right. Put that over here, negative delta H over T squared. Now we have a function where we have, we can kind of work it out from here, right? So if we wanted to do this, right? If we wanted to do this, let's rewrite this a little bit and make it a little bit more obvious. All right, this is left-hand side is 73.1 over T squared, right? That's what T to the negative 2 means. Left-hand side is negative delta H over T squared, right? When you put it this way, it becomes fairly obvious, right? T squared on the bottom, T squared on the bottom, they cancel each other out, right? So 73.1 equals negative delta H, which means that our delta H has to be negative 73.1. And in this case, let me see what the units are given. This is 3B. This is in joules. All right, I should include that. This is in joules. That's what it says in the book, right? So our delta H for this would be negative 73.1 joules, right? So this is how we would use this if we needed to use this, right? We have an equation for delta G, a line fitted graph basically, divided by T, do a derivative of that entire left side, and that's going to be equal to more normal math on the right side, basically. So delta H equals negative 73.1 joules. Right? Joules. And that's all we would need to do this, right? It looks super complicated until you realize that this is literally just division. And then you do a little bit of division, you do a little bit of derivative, bing, bang, boom. Not terrible, right? Not terrible at all. Now, moving on from there, if we wanted to look to see how the Gibbs free energy changes with pressure, right? Because this is, if we looked at it, right? We have pressure, we have temperature. I'm looking at both of them, right? This is how it changes in temperature. This Gibbs Helmholtz, right? How does it change with pressure? Right. So if our temperature is constant, right, and dT is 0, then dG is equal to VdP, right? So we had dG equals, what was it? It was negative SDT, right? dG was VdP minus SDT, right? Well, if dT is 0, temperature is constant, right? Then dG is VdP, right? If we integrate this, right, then we would get G at the final pressure equals G of the initial pressure plus basically our change here, right? Basically our change, right? Which we would end up being, in this case, V times PF minus PI, right? If we integrated that, that's what we would get. V times PF minus PI. Right? If we want to do molar quantities, same difference, right? It's just molar, molar, molar for our Gibbs free energy and for our molar volume. And same difference. All of this here would become, right, Vm times Pf minus Pi. Right? Simple little bit of integration there. Right? Luckily, most of these integrals are fairly simple. Right? Now, if we look at this particular equation here, right? Since solids and liquids are largely incompressible, right? We are kind of, when we do this, right, we are assuming that Vm is going to be basically constant. Because if it wasn't constant, we couldn't do this integral, like, Vm stays intact, if you want to call it, because we're assuming it's basically constant, right? If it wasn't, then we have to include the change in Vm with the change in pressure. It'd be a lot more complicated. We'll get there. All right. For solids and liquids, though, right, this is a pretty good assumption, right? If you look at this, this figure here, right, the difference in Gibbs energies of a solid or liquid between two pressures is like the actual variation in it is very small, right? Very small. Since it says assumed to be negligible. That's because Vm, while not technically constant for a solid or a liquid, is practically constant, right? And so put it all together and we get this, right, for solids and liquids, right? For solids and liquids specifically. Now, if we want to talk about gases, it's going to be a little bit more complicated, right? But we're going to do that in a minute. So this is the change in Gibbs energy of 1 cubic decimeter of liquid octane. And the pressure acting on it is increased from 1 atmosphere to 100 atmospheres. Given that the mass density of octane is 0.703 grams per centimeter cube, determine the change in the molar Gibbs energy. Okay, so what we want to do, right, we want to be going here. So let's start with Gm at, we'll call it P2 equals G molar at P1 plus B molar times P2 minus P1, right? That's what we just saw. PF, PI, 2 and 1, same difference. Right. Now again, we did this before in the last video, right? If we move G molar at P1 over, subtract it, right, then we would get delta G is going to be B molar times P2 minus P1, right? Okay, so what we need to do this is two different pressures, which we have, right? We have 100 atmospheres, we have 1 atmosphere, right? That'll work. And then we need a value for V molar. Well, we have a value for volume, but not a value for molar volume, right? So let's start there. Just to be super safe, let's change our molar volume into cubic meters, right? So our volume is going to be equal to 0.001 cubic meters, right? Let me double check that. 1 divided by 10, divided by 10, divided by 10. Yes. All right, our volume is 0.001 cubic meters. All right. If our mass density is 0.703 grams per centimeter, or basically our density, which is rho, this is rho, I can't remember how to draw rho. It's like kind of like a Q. Oh no, I remember that's rho. It's like a squiggly P. Right, is 0.703 grams per centimeters cubed. Right. Then 1 decimeter cubed is going to I have to change that to centimeters cubed times 0.703 grams per centimeters cubed. Right, that is going to be how many grams? It's going to be 1,000 times 0.703, which is 703 grams of octane, right? 703 grams of octane. Right, change that into moles. Well, let's see. In 1 mole, there is going to be, let's see, C8, 12 times 8 plus H. It's 12 plus 6, 18. Right, so the molar mass should be 114 grams per mole. All right, you do that. 703 divided by 114 gets me 6.16. We'll just keep it there. Moles of octane. All right. And then the molar volume. Whoop, go back. Right. The molar volume is going to be our 0.0. Wait, that's not the right one. Our molar volume is going to be. Sorry. 1 second, I got a call. Sorry about that. You know, despite my kid being expected still like more than a month from now, every time I get a call from my wife, I have to answer it. But anyways, so our molar volume, right, is going to be volume divided by moles. Is going to be our 0.001 meters cubed divided by our 6.16 moles, right? Which will give us a value of 1 divided by 6. We'll give a value of, we'll do 1.62 times 10 to the negative 4th, right? Meters cubed per mole. Right. So we have values of Vm and meters cubed per mole. Right. Now for our pressure is given to us in atmospheres. Now, unfortunately, because this is subtraction and not division, we got to be a little bit more careful about our units, right? Since we did meters cubed per mole, right? Let's change our atmospheres into pascals to keep it all on the same playing field, right? Right. So, right, 1 atmosphere is going to be 101,325 pascals, right? And 100 atmospheres is going to be 101,32500 pascals. See, I just added 2 more zeros on it. Right. So if we wanted to do the math here, right, our delta G is going to be molar volume of 1.62 times 10 to the negative 4th times 101,32500 minus 101,325. Put that all together. What will our answer be? Let's see. So 1.62 e negative 4 times 101,32500 minus 101,325 gets me a delta G of 1.625 times 10 to the 3rd joules. Right, 10 to the 3rd joules. Right. And if you look at it, 10 to the 3rd joules, that's the same thing as 1.625 kilojoules. Right? And most often, delta G is given in units of kilojoules per mole. Right? And this is technically per mole because this mole still sticks around. Kilojoules per mole. Right? And this is for solids and liquids. Now, if we have a gas, slightly more problems. Here we go. Right, we expect the molar volume to vary dramatically as the pressure changes. Right, but for a perfect gas, right, we know that our molar volume is still going to be RT over P. Right, if it were not a perfect gas, if it were like a Van der Waals gas, it would be more complicated, right? Be much more complicated than trying to solve for VM, right? Get messy. Right? If we put this in for VM, right, what do we see? Well, now we have the same thing, but now we have, instead of VM dP, now we have RT over P dP, right? RT is the constant, it comes out, right? The integral of 1 over P with respect to P is always going to be the natural log of, in this case, PF over PI, right? That's our 2 limits. All right, those are our 2 limits. Now you notice this, again, this one, super useful, looks very, very, very similar, right, to what we've seen before. Oh, going 1 second. Well, I hate when it does that. Right, I just wanted to go backwards, right? But it's very, very similar to what we saw for S, right? Very similar to what we saw for that. Very similar to what we saw for H, right? Again, since all these things are state functions and they're all interrelated, then we would expect that to happen. All right, let's go down here. Let's turn our thing back on. Be quiet. There you go. So if we wanted to calculate the change in Gibbs index for a perfect gas, when the pressure is increased from 1 atmosphere to 100 atmospheres at constant temperature, right, as we just saw, right? Same thing we do before. Right, we have G, second, right? G at, we'll call it pressure 2, equals G at pressure 1 plus RT natural log of PF, we'll call it P2 over P1, right? And as we have done before, right, we move G at P1 over, the whole thing becomes delta G, right? RT natural log of P2 over P1. PF over PI, same thing as P2 over P1, however we want to do it, same difference. Right. Now from here, this is actually going to be a little bit easier, right? We don't need to do any conversions. Right, we don't need to do any conversions. Right, R can just be plain old 8.314 joules per mole Kelvin. Right, temperature we are told is 298 Kelvin. Right, and then for our natural log, because they are actually divided, we can just put in straightforward 100 atmospheres over 1 atmosphere. Right, we can just put that in, no problem. Right? Because again, when you divide them, the units are going to cancel out, and our log always has to be dimensionless. Right? We put all of these together, do a little bit of math. You're going to have, see, the natural log of 100, right, times 298 times 8.314, which will get us a value of 1.14 times 10 to the 4th joules, right? 1.14 times 10 to the 4th joules, or 11.4 kilojoules per mole. Right, 11.4 kilojoules per mole. All right, again, fairly straightforward. Right, luckily fairly straightforward. And if you compare this to the number we got for our solid and liquid thing, right? This was a smaller number, which we would expect, right? A gas undergoes a greater change whenever we change the pressure, so we would expect a greater change in delta G, right? That's what the whole point of these graphs were, right? When we change the pressure, we expect a bigger value of the change in delta G for gases versus liquids and solids. But that's it for this topic. All right, hopefully it's a little bit of a break from everything else, like the last 2 topics, honestly. It's a little bit easier. I'll be making and getting everything ready for the next topic, which is, if you've looked it up, there's only 4A, 4B, and 4C. So it's a pretty small number of sections, and they're not very big. Let's see. 120. Yeah, the next topic, which is the only other topic on this exam, is going to be just 20 pages by itself. So we'll get there. Other than that, keep on keeping on.